This is SpaceTime, Series 20, Episode 66, coming up on SpaceTime. The Moon's magnetic field lasted longer than previously believed. Is the universe's dark matter disappearing? And a new type of supernovae. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
New evidence indicates that the Moon's magnetic field may have lasted up to 2.5 billion years longer than previously thought. The findings, reported in the journal Science Advances, has major implications for life and habitability on other moons and planetary bodies. Planetary magnetic fields are important because they act as shields, protecting a planet's atmosphere from being damaged or blown away by stellar winds. They also provide a significant barrier against ionizing radiation. This makes planetary magnetic fields important factors in any search for life. The study's lead author, Assistant Professor Sonia Taiku from Rutgers University, says without this shield, the Earth would be subjected to more radiation, resulting in more mutations. She says we just don't know how life would respond in such a harsh, unstable environment. When a planet's magnetic field dies, ionizing particles from its host star can also lead to a loss of water over time. And that presents another big deal in terms of habitability. The Earth's magnetic field is generated through a geodynamo, produced by the planet's spinning liquid iron outer core. A planetary magnetic field will die off once the core cools down and solidifies, leaving only remnant magnetism imprinted in any molten rocks exposed to that field. A good example is the red planet Mars, which went from a warm, wet world with a thick atmosphere and a habitable environment suitable for life, into an inhospitable freeze-dried desert once its core solidified some 3 billion years ago. Taiku began working on the study as a grad student at MIT back in 2013. To determine the exact age when the lunar magnetic field stopped, Taiku and colleagues examined lunar rocks brought back by the Apollo moon missions. Their examination included heating a lunar rock to retrieve an accurate intensity for its lunar magnetic field. Taiku reanalyzed the moon rock collected by the Apollo 15 crew on August 1, 1971, on the southern rim of Dune crater within eastern Mare Imbrium. The small young rock, partially coated with melted glass, likely formed during a meteor impact on the lunar surface. Taiku used a rock magnetometer to analyze the lunar rock. The device measures the strength and direction of magnetic fields within rocks. She slowly demagnetized the rock to reveal its original magnetization, heating it to some 780 degrees Celsius in a controlled environment chamber at MIT to keep the heat from altering the rock. The researchers think the moon's magnetic field declined by about 90% from its high point some 3.56 billion years ago or earlier. That's when the moon's magnetic field was at about the same strength as Earth's magnetic field is today, an average of about 50 microtesla, which is a measure of magnetism. The lunar rock Taiku tested, which is between 1 billion and 2.5 billion years old, recorded 5 microtesla. The moon has no core-generated magnetic field today, and scientists don't know when it turned off. Lingering questions include trying to figure out exactly when the field ceased and what the field was like between 3.56 billion and 2.5 billion years ago. The authors didn't think small planetary bodies such as the moon could generate magnetic fields for very long. That's because, as well as having smaller overall bodies, they likely have smaller cores as well. Consequently, they would cool down quickly and crystallize early in their lifetimes. Because the rate of crystallization depends on the core's composition, these findings may challenge science's current hypotheses about the composition of the lunar core. The moon's core is mostly made of iron, but other things must be mixed in there with it, possibly sulfur, carbon, or another element. Taiku says whenever scientists look at exoplanets, or for that matter the moons of exoplanets that could be in the habitable zone of their host stars, the region where it's not too hot and not too cold but just right for liquid water to pool on the surface, they also need to consider the magnetic field of that body as an important player in habitability. She says the question then becomes what size planets and moons scientists should be considering as possibly habitable worlds.
The moon falls into an interesting intermediate size range between planetary bodies that currently still have magnetic fields, like the Earth and Mercury, for example, and very small planetary bodies like asteroids, which used to have magnetic fields at the beginning of the solar system that died out, like within the first few hundred million years. And so because the moon kind of fell in the middle, it presented an interesting target to really test how long magnetic fields could last on intermediate-sized planetary bodies.
Okay, so by understanding this, you understand a little bit about how the lunar interior has evolved over time too, I guess.
Right, because in order to generate a magnetic field, you have to have motion of the fluid in the core of the bodies. So you have motion of this conducting metal in the core. And by studying the moon and its very long-lived magnetic field, as we're showing now, we can figure out what the mechanisms are that might have been driving fluid motion in its core and how that may extend to other bodies that are in a similar size range.
I guess the key phrase there is just how long the lunar magnetic core's been around, at least 1 billion, possibly a lot longer, compared to what was previously thought.
Yeah, so before, in previous studies, researchers had shown that the lunar magnetic field lasted until at least 3.5 billion years ago. So given that the moon formed about 4.5 billion years ago, it lasted from at least 4.25 to about 3.5 billion years. So we knew it had lasted for 750 million years, and by this study we showed that the field persisted till at least 2.5 billion years ago. So we added another billion years onto what had previously been established.
And that's somewhat of a surprise because if the geodynamo, as most scientists now accept, is caused by the rotation of molten liquids in the core of a body, then you'd expect a certain standard rate of cooling depending on the chemical formulation of that core and the size of the body itself. And that doesn't sort of match up with what we're seeing on the moon, which must tell us something about the way the internal structure of the moon is.
Right, because as you explained, the generation of the magnetic field and the fluid motion in the core is tied to the cooling rate of the core and also what elements are contained in the core. So we know that the lunar core is likely less than about 400 kilometers radius, and then that's out of a 1,700 kilometer radius body. So it's a small core. We know it's mostly made out of metallic iron, but there may also be some other light element like sulfur or carbon mixed in with that iron. And what we're going to have to do now is we're going to have modelers who look at how core composition affects the longevity of the dynamo, coupled with looking at the radius of the core. And the modelers are going to try to figure out how to reproduce long-lived magnetic field using what constraints we know about the core right now. And there are a couple papers, actually, that show that we might be able to generate a dynamo lasting this long, either continuously or intermittently, using crystallization of the inner core as the power source. But it's going to take more work before we can reproduce the intensity that we got from the sample that we studied in this project. Because in this project, we showed that at least 2.5 billion years ago, or later, perhaps up to 1 billion years ago, the field was 5 microtesla. That's the magnetic field unit that we use. And the model so far can only reproduce less than 1 microtesla. So making the intensity catch up to what we observe is going to be the next problem.
You guys have come up with some hypotheses as to what may have been going on, and one of those involves 2 separate causes for the generation of the magnetic field in the first place.
Right. So right now in this paper, we're sort of talking about the later portion of the lunar dynamo, closer to when the field might have ceased. But our previous studies show that before 3.5 billion years ago, during the period 4.25 to 3.5 billion years ago, the lunar magnetic field might have been as strong as the Earth's magnetic field is today, around 50 microtesla, which is 10 times higher than the field we measured in this younger sample. And so that high value it's way higher than what models are capable of generating for a field intensity based on core cooling. So that tells us that early in lunar history, we may have required an additional power source contributing to the dynamo. And one power source that has been proposed is that earlier on, more than 3.5 2.5 billion years ago, the moon was much closer to the Earth than it is today, and it's been receding away from the Earth over time due to tidal interactions. But when the moon was closer, the Earth's gravity may have been pulling more strongly on the lunar mantle and causing the mantle to kind of wobble back and forth. And it's thought that perhaps that wobbling could have led to stirring of the core mechanically, and that could have generated a powerful dynamo field.
Giving you the extra heat as well, yeah.
Yes.
How does one measure the magnetic field in the moon when you're here on Earth? How did you guys do it?
What we did was we studied samples, rock samples that were collected from the Apollo missions. And over the past few years, we've, as a community, have measured several samples of different ages. So what we do is we take the rock and we can put the rock in a magnetometer, and that magnetometer can measure the direction and intensity of the magnetization that is preserved in the rock that was acquired at the time that the rock formed. So whenever rocks form, they contain little mineral grains that record whatever magnetic field is around. And so when we measure the magnetization in the rock, that gives us information about what the strength of the magnetic field was at the time that the rock initially formed.
Okay, so that should theoretically tell you what it was like when the moon formed, and it was just a magma sea and eventually solidified to give us the moon we have now. There are other methods that cause rocks to melt. One of those is asteroid impact, and that's really what you guys were sifting through and looking for the right rocks to give you a more recent look at what the moon was going through.
Right. So just to clarify, we don't actually have rock dating back to the initial formation of the moon, but we have lots of rocks that formed from later processes, such as the formation of the moon's crust or from lava flows that erupted onto the moon's surface. And in this case, the sample we studied was a sample that formed by melting of pre-existing rocks by a meteorite impact. And so what was great about this rock was because it melted from a meteorite impact and cooled down very quickly, because it was just at the surface of the moon and it could cool down very fast. It had very small magnetic grains, which are exceptionally good magnetic recorders. In general, the smaller the grain, the better the magnetic recording capability. And because it was an exceptional recorder, it could provide an exceptional record of the ancient lunar magnetic field.
And how do you actually go about working out how good a recorder a specific sample might be? You have to perform some tests on it.
Right. So basically what we do is we take a sample that we may have already demagnetized during an earlier experiment, and we impart that sample with known magnetic field intensities, and then we check the magnetic behavior of the sample to figure out, we do a test, which is basically the same test that we figure out what the ancient magnetic field intensity was in a natural sample, and we try to see if we can retrieve the same intensity as the field that we gave the sample. So if I give the sample a 5 microtesla field magnetization and we run an experiment to determine the paleo intensity, we should get 5 microtesla again. So we're trying to see how weak of a field we can impart the sample with and successfully retrieve a stable magnetization from that sample.
That's Assistant Professor Sonia Taiku from Rutgers University in the United States. And this is Space Time. I'm Stuart Gary. A new dark energy study suggests the amount of dark matter in the universe may be decreasing. The new findings are based on data from the Victor M. Blanco telescope showing a discrepancy between data in the early universe and what we see in the local cosmos today. The data, using results from the Dark Energy Survey of the Southern Skies, could have major implications for science's understanding of physics and the ultimate fate of the universe. Dark matter and dark energy are so called because science has very little understanding about what they are, even though combined they make up almost 96% of the total mass energy budget of the universe. Dark energy is a mysterious force, causing the expansion of the universe out from the Big Bang 13.8 billion years ago to accelerate. There are numerous hypotheses to try and explain it, the latest being vacuum energy caused by the quantum fluctuation of virtual particle pairs popping into and out of existence. Dark matter involves some sort of invisible substance which appears to only react gravitationally with normal matter. The stuff stars, gas and dust clouds, planets, asteroids, houses, cars, dogs, cats and people are made out of. Scientists know dark matter exists because they can see its influence on normal matter holding galaxies together. The Dark Energy Survey is revealing how matter is distributed through 26 million galaxies across a huge chunk of the southern skies. Astronomers compared the new data to observations of the early universe made in 2013 by the European Space Agency's Planck spacecraft in order to see how the universe was evolving. The comparison would also help scientists predict just how the cosmos would continue to evolve into the future. However, when they compared the two sets of data, they discovered a mismatch. The Planck data indicates 34% of the early universe was made up of dark matter, whereas the Dark Energy Survey data indicates today's universe only has about 26% dark matter. Astronomers say the mismatch could resolve itself as more and more data becomes available during the Dark Energy Survey's 5-year observational run. Still, it's not the first surprise to have come up in this area. The Planck data also demonstrates inconsistencies when compared with observations from the South Pole Telescope in Antarctica. Overall, the findings are intriguing because they have important implications for the ultimate fate of the universe. You see, with the right proportion of dark energy, dark matter and normal matter, the universe will remain in a steady state, looking similar to what we see around us today. The problem is, science's current understanding says that simply ain't going to happen. If there's an increase in the amount of matter compared to energy, then the universe could start to gravitationally collapse in on itself, eventually resulting in a big crunch, which could in turn cause another big bang and the creation of a new universe, and possibly repeated cycles of big bangs, expansion, contraction and big crunches. But again, based on current observations, that's also impossible. So what's left? Well, the only real option is an ever-expanding universe, at least based on the data we now have. The most likely option involves the accelerated expansion of the universe causing galaxy clusters to eventually drift away from each other beyond the visible cosmic horizon. So far away, in fact, that light from these distant clusters will never reach us again, leaving isolated groups of gravitationally bound galaxies surrounded by the vast emptiness of nothing. A possible future a few trillion years away, which astronomers are calling the Big Freeze. However, if the new observations of a reduction in the proportion of dark matter in the universe are correct, then the accelerated expansion of the cosmos will quickly overcome the gravitational force of dark matter holding things together. That will result in not just galaxy clusters moving away from each other, but the galaxies themselves breaking apart, as will the star systems inside them. In this so-called Big Rip scenario, the accelerating expansion of the universe will also overpower the fundamental forces of nature, causing stars and planets to tear apart, and eventually even atoms will be ripped apart into their constituent subatomic elemental particles. And this Big Rip scenario would also happen a lot quicker than the Big Freeze, taking just a few billion years to unfold, meaning the universe we know today may already be in its senior years. Something to ponder when you go to bed tonight. Pleasant dreams. This is Space Time. I'm Stuart Gary. If you want more Space Time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook just go to www.facebook.com/Spacetime with Stuart Gary. Astronomers have identified a white dwarf that may be the leftover remains of a recently discovered type of supernova. The findings, reported in the journal Science, indicate that the properties of this unusual white dwarf, known as LP4365, may help scientists determine how such unusual supernovae are created. A white dwarf is the stellar corpse of a dead Sun-like star. Once a star like the Sun runs out of the nuclear fuel it needs for core fusion, it expands into a red giant. Eventually, its outer layers are puffed off, leaving only a white-hot super-dense stellar core of oxygen and carbon, a white dwarf, which will slowly cool over the eons of time. Now, If this white dwarf happens to be in a close binary orbit with a companion star, then the white dwarf will gradually draw material off the companion. When enough of this drawn-off material settles on the surface of the white dwarf, it'll reach pressures and temperatures high enough to undergo thermonuclear detonation, causing the star to suddenly brighten dramatically as a nova, or new star, while the scavenged material explodes. Then the white dwarf keeps drawing more material off the companion star, and the cycle is repeated. However, if the white dwarf draws off enough material from the companion star to reach a critical mass of about 1.4 times that of the Sun, what's referred to as the Chandrasekhar limit, then the explosion will be so catastrophic that the white dwarf will be destroyed in what's known as a thermonuclear or Type 1a supernova, an explosion so powerful that it will briefly outshine an entire galaxy. Because all Type 1a supernovae explode with roughly the same mass, 1.4 times that of our Sun, then it means they must also exhibit about the same level of luminosity or brightness, and that makes them useful as standard candles to measure cosmic distances using the inverse square law. It's the same sort of effect you get when looking at a row of streetlights along a road. You get an idea of how far away each of those streetlights are by simply looking at how bright it appears when compared to the others. This quality has made Type 1a supernovae important in determining not just cosmic distances across the sky, but also the accelerated expansion of the universe, and therefore the discovery of dark energy. Recently, astronomers have discovered a related type of supernova which they're calling a Type 1ax. It looks like a Type 1a supernova, but it's much fainter. Type 1ax supernovae may be caused by the partial destruction of a white dwarf star in such an explosion. We're talking about something in between a supernova and a nova. Now, if that interpretation's correct, then part of the white dwarf should survive the explosion. Scientists have identified LP4365 as an unusual white dwarf. It has a very low mass, a high velocity, and a strange composition. And that's exactly what might be expected from the leftover star of a Type 1ax supernova event. They calculate the explosion must have occurred between 5 and 50 million years ago. You're listening to Space Time. I'm Stuart Gary. Astronomers have discovered two detached eclipsing white dwarf binaries which could one day merge to form an exotic type of star known as an R corona borealis. The discovery, reported in the Astrophysical Journal and on the pre-press physics website archive.org, could also provide a new target in the hunt for gravitational waves. The system, whose components have orbital periods of 40 and 46 minutes respectively, was discovered by astronomers using the MMT 6.5 metre telescope on Mount Hopkins in Arizona, which is jointly operated by the Smithsonian Institute and the University of Arizona. A white dwarf binary is a system containing two white dwarfs orbiting each other. Being detached means the two white dwarfs aren't close enough yet to draw mass off each other. And eclipsing binaries simply means the two stars are orbiting each other in such a way that one passes in front of the other or eclipses it, as seen from Earth. It was observations from the Apache Point Observatory's 3.5 metre telescope which revealed that one of the binaries was an eclipsing binary, making it only the seventh known eclipsing white dwarf binary system. And only a handful of white dwarf binaries are known in the Milky Way to have orbital periods less than an hour. Because of the structure of the system, white dwarf binaries would have a fair bit of gravity associated with them. And that means, as well as merging black holes and neutron stars, short-period double white dwarf binaries would also be capable of generating very detectable gravitational waves. In fact, the new discovery should be emitting so much gravitational wave energy that it's likely to become a verification source for the upcoming Laser Interferometer Space Antenna gravitational wave satellite. Astronomers are now keeping a close eye on their discovery as the stars eclipse to measure just how quickly they're getting closer to each other. That will provide clues as to how soon they'll merge. As to what happens when the white dwarfs finally make contact, that's still a mystery for now. The most likely result would be a supernova explosion. However, another possibility is that the white dwarfs will merge to form an exotic new type of star called an R corona borealis. These stars are often identified by their spectacular declines in brightness at irregular intervals. Out of the billions and billions of stars in the Milky Way galaxy, only about 65 have been identified as our corona borealis. As to when all this happens, well, no one's sure. The best estimates indicate that double white dwarfs could be expected to merge sometime within the next 20 to 35 million years. I'm Stuart Gary. This is SpaceTime. NASA has launched its latest TDRS communications satellite. The Tracking and Data Relay Satellite M blasted into orbit aboard a United Launch Alliance Atlas V rocket from Space Launch Complex 41 at the Cape Canaveral Air Force Station in Florida.
All systems are go.
9, 8, 7, 6, 5, 4, 3, 2, 1. And we have liftoff of TDRS M on the Atlas V rocket from Space Launch Complex 41. TDRS M, securing space-to-ground communication for NASA's low Earth orbit operations, including the International Space Station.
Atlas beginning engine yaw maneuver to steer to its planned path at an inclination of 26.2 degrees. You're hearing the voice of Patrick Moore providing launch vehicle ascent data. Patrick is the United Launch Alliance Denver Network Operations Center Command Control Center.
Pump speeds and injector pressures all looking good. Now
Reading the
passing
data
45
coming directly
seconds
from the
into
rocket.
flight.
The Atlas rocket carrying TDRS
nominal
M
flight
reached
control
supersonic speed at 1 minute and 20 seconds into flight.
Now passing 1 minute into flight. Vehicle is now 3 miles in altitude and traveling at 1,100 miles per hour.
Standing by for max Q. Or
Now passing 1 minute 15 seconds into flight.
32 seconds into flight.
Mach 1, Atlas V is now supersonic. 1 minute 30 seconds into flight. Now passing through max Q, maximum dynamic pressure.
This is the point when mechanical stress on the rocket reaches its peak because of the rocket's velocity and resistance created by the
The
atmosphere.
RD-180 is throttled down to 95% thrust as expected. Engine response looks good. This engine thrust profile will continue until the vehicle reaches a programmed 5G acceleration limit.
About 2 minutes into the flight
And
of
now
Atlas.
passing 2 minutes into flight, approximately 2 minutes remaining in the first stage of flight. Vehicle trajectory traveling right down the middle of the range track, looking good. RD-180 engine operating parameters also looking good.
Booster engine cutoff slated for 4 minutes 2 seconds after launch.
The Atlas V rocket now weighs just 1/2 of what it did at launch, burning propellant at a rate of almost 2,600 pounds per second. And vehicle has gone to closed-loop guidance, now passing 2 minutes 30 seconds into flight. And RCS pyro valve has been fired. Centaur reaction control system is now pressurizing the flight levels. Atlas V is now 30 miles in altitude, 43 miles downrange distance, traveling at 4,700 miles per hour. And now passing 3 minutes into flight, approximately 1 minute remaining until booster engine cutoff. RD-180 continues to perform well. Vehicle trajectory continuing down the middle of the range track.
ULA's Patrick Moore providing vehicle ascent data.
Now passing 3 minutes 30 seconds into flight, Mach 10. And vehicle has reached the 5G throttle limit, and we've begun boost phase chill down.
Less than 30 seconds away from booster engine cutoff.
3 minutes 50 seconds into flight, standing by for BCO momentarily.
6 seconds after BCO, the Centaur second stage will separate from the Atlas booster.
And we have BCO, booster engine cutoff, standing by for stage sep.
10 seconds after
And we
separation.
have good indication of stage separation.
The Centaur
have
single RLC engine ignites for the first time.
We have ignition and full thrust on the RL-10.
The RL-10 produces 22,900 pounds of thrust and burns for just under 8 minutes.
And we have good indication of fairing separation. This is the first of 2 planned burns for today's mission. This first burn should last approximately 13 minutes and 40 seconds.
The payload fairing protecting TDRS-M during its flight through the atmosphere
And
has been
RL-10 engine
jettisoned.
operating parameters all looking good. Vehicle trajectory continuing down the middle of the range track. The Centaur is now 107 miles in altitude, 350 miles downrange distance, traveling at 11,160 miles per hour.
The TDRS-M satellite is the third and final member of the constellation of third-generation spacecraft. Following its deployment from its Centaur upper stage, the TDRS-M began a 6-month testing calibration period. Once that's complete, it'll be renamed the TDRS-13 and be listed as operational. The 9-satellite TIDRAS constellation provides continuous communications between NASA, astronauts in flight and aboard the International Space Station, and NASA's fleet of orbiting satellites and space telescopes such as Hubble. The satellites are placed into geostationary orbits, providing continuous broadband communications with NASA ground stations at White Sands, New Mexico, and at the US Pacific Island territory of Guam. The first TIDRAS satellite, TIDRAS-A, was launched aboard the Space Shuttle Challenger on mission STS-6 back in April 1983. The networks replaced the need for patchy ground, ship and aircraft-based communication systems, which were often limited by local weather conditions. You're listening to Space Time. I'm Stuart Gary. A Russian Proton rocket has launched a top-secret military payload into orbit. The 58-metre-tall Proton M launched just before dawn from the Baikonur Cosmodrome in the Central Asian Republic of Kazakhstan. The clandestine payload is believed to be the new Russian Ministry for Defense Blagovest high-throughput telecommunications satellite. It's a highly classified project, so let's tell you all about it. Blagovest uses a Russian Express 2000 satellite platform. It's been fitted with Thales-Alenia space communications payloads equipped with C-band and Ka-band transponders, as well as one of the first spaceborne applications of the new generation Q-band transponder system, designed for high-throughput broadband communications. There are still a lot of problems to be ironed out with Q-band for space-based applications, so this is quite a daring move by the Russians. The 4.5-ton Blagovest 11L satellite uses both chemical and electric propulsion systems for orbital maneuvering and station keeping, and carries enough fuel for an 11-year lifespan. Proton's Breeze-M upper stage placed the satellite into a classified geostationary orbit, which we know happens to be at 45 degrees east longitude. The mission was only the second launch for the Proton since returning to flight status earlier this year, following a series of failures by the Russian Federal Space Agency Roscosmos in recent years. Most of those have been put down to quality control issues during the rocket's manufacturing phase. It was also the 100th launch of a Proton M series rocket, and the 414th flight of a Proton rocket series since the maiden flight back in 1965. Spreading the word on all of Russia's classified news, this is Space Time. I'm Stuart Gary. And time now to take a brief look at some of the other stories making news in science this week with a science report. And a new study claims there are no major differences in gender identity development of children raised by same-sex couples compared to those adopted by heterosexual couples. The findings by scientists from the University of Kentucky is based on a study of more than 100 families with either gay, lesbian or heterosexual parents. Researchers looked at the kinds of toys children preferred to play with during their preschool years. That's seen as indicators of whether the kids will grow up to conform to typical gender stereotype norms or not. The researchers observed the play styles and the toys that the family's preschool children preferred during playtime. The study included 5 years of follow-ups. The types of play and behaviour that most children display are found to be typical of their gender and already appears to be set in motion from early childhood onwards. Preschool kids who played more with toys that are not typically assigned to their sex were in later school years more likely to aspire to jobs and other preferred activities that are not typically ascribed to their gender. The new study found that the family structure had little influence on how children's sense of gender developed. Moreover, little truth was found in the idea that lesbian or gay parents might encourage or allow more gender nonconformity among their children. The study found that parental sexual orientation and family type did not affect children's gender conformity or nonconformity in any significant way. Earlier this year, Arctic sea ice levels sank to a record low wintertime extent for the third straight year in a row. So now, NASA are flying a set of instruments north of Greenland to observe the impact of the melt season on the Arctic's oldest and thickest sea ice. Known as Operation Icebridge, NASA's airborne survey of polar ice launched a short campaign last month from Greenland. Weather permitting, the Icebridge scientists are hoping to complete 6 4-hour flights focusing on sea ice that has survived at least one summer. This multi-year ice, once the bulwark for the Arctic sea ice pack, has dramatically thinned and shrunk in extent along with the planet's warming climate. In the mid-1980s, multi-year ice accounted for some 70% of all Arctic winter sea ice coverage. However, by the end of 2012, this has dropped to less than 20%. Most of the Arctic Ocean used to be covered in a thick multi-year ice sheet, which wouldn't completely melt during summer and thus would reflect back a lot of sunshine. But man-made global warming has caused the loss of most of this old ice, exposing the open ocean below, which absorbs most of the sun's energy. Scientists say this could explain why Arctic warming has increased at nearly twice the global average. They say when Earth loses its reflective cover over the Arctic Ocean, it's losing another mechanism to cool the planet. A new study has confirmed what most people have already suspected. Teenagers who smoke e-cigarettes are 4 times more likely to take up smoking regular cigarettes in the future. The findings, reported in the journal Tobacco Control, suggest that experimentation with e-cigarettes may act as a gateway to smoking regular cigarettes in adolescence. The research teams examined 2,386 teens from 20 schools across the UK when the respondents were aged 13 and 14, and again a year later. At baseline, nearly 2/3, 61.5% in fact, that's 1,726 kids, had neither tried vaping nor smoking. 16% said they had tried e-cigarettes, 4.4% had tried smoking but not e-cigarettes, and nearly 1 in 5, that's 18.1%, had tried both. The researchers found that starting to smoke over the next 12 months was significantly more common among those kids who had friends and family members who were smoking. But more surprisingly, it was also strongly associated with e-cigarette use, especially among those without friends that smoked. And that's a group that's usually thought to be less vulnerable to taking up smoking. Among those who had never smoked cigarettes but had tried e-cigarettes at baseline, a third, 34.4%, admitted they had tried cigarettes within the next 12 months, compared to only 9% in the group who had not tried e-cigarettes at baseline. After taking into account other potentially influential factors, those who vaped were 4 times more likely to start smoking conventional cigarettes compared to those who didn't use e-cigarettes. And occasional smokers at baseline were nearly twice as likely to escalate their habit if they had tried e-cigarettes, compared to those who hadn't experimented with vaping, just over 24% compared to just under 13%. While North Korea has taken a step back on its nuclear threats against the United States, its axis of evil partner Iran is continuing to escalate tensions, building a new missile factory in Syria. New spy satellite images have confirmed that work on a new Scud missile plant is well underway near the city of Banias. Images show construction of the plant began last year, and it will probably be operational by year's end. Intelligence experts say the new plant's almost identical to the construction methods used in similar factories in Iran. Iran's a strong supporter of Syrian dictator Bashar al-Assad and his backers in the Hezbollah terrorist group. Tehran's been providing both with financial aid and military help. The move is part of a program to expand Iran's control across the Middle East through proxy forces in Syria, Lebanon, Iraq and Yemen. It comes despite the 2015 non-proliferation agreement signed between Tehran and the Obama administration. That deal was designed to stop Iran's nuclear weapons and missile programs. However, Iran's parliament has just voted overwhelmingly to raise spending on its military and missile programs. The vote was Iran's response to legislation passed by the US Congress and signed into law by President Donald Trump earlier this month to impose new sanctions on Tehran for violating the agreement. 2 160-million-year-old mammal fossils discovered in China show that the forerunners of mammals in the Jurassic period evolved to glide and live in trees. With long limbs, long fingers, long toes, and wing-like membranes for gliding tree to tree, the pair are the oldest known gliders in the long history of early mammals. The new discoveries suggest that a flying way of life evolved among mammalian ancestors 100 million years earlier than the first modern mammal flyers. The fossils are described in 2 papers published in the journal Nature. The ability to glide between trees allowed ancient animals to find food that was inaccessible to other land-based animals. That evolutionary advantage can still be seen among today's mammals, such as bats, flying squirrels, and sugar gliders. And finally, for now, a new study shows that older adults are drawn to Facebook to check out images and updates from their family and friends, but they may resist using the website because they're worried about privacy and who'll see their own content. The findings, reported in the journal Telematics and Informatics, suggest Facebook developers need to focus on privacy settings in order to tap into the senior market. The study also found that older adults tend to see many of the conversations on Facebook as being trivial, with people reporting on the mundane and unremarkable things they do. Researchers found that while the 55-plus age group was slow initially in adopting social media, they're now one of the largest growing sectors for social media adoption. Researchers recruited 46 participants who were aged between 65 and 95 to take part in in-depth interviews. The group included 20 participants who were already on Facebook and 26 who weren't. 17 of the participants were male, 29 female, and all of them had a college degree and were already using computers in their daily lives. You're listening to Space Time. I'm Stuart Gary. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more space time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts, or Audio Boom. This has been another quality podcast production from Bytes.com.